about is crop production in Australia in a very dry environment. But I want you to think of what I talk about is somewhat irrelevant. I guess what I want you to be thinking about, whatever system you're working in, is what kind of a farming system might you need to put around your deep roots once you know they're working and they're operating well. What's the systems thinking that might need to go around them to get value from them? And I guess the universal questions that I think Christian started with and that we're all thinking about is are roots function at depth, and whether that's 2 to 5 or depends on your context. Can you capture benefits in whatever production system, whether that's trees or crops? And then I guess I come back at the end to Peter's question about what's the scale of this opportunity globally to capture value. And the case study I'm going to be talking about is deep water use in Australian dryland farming, which for reasons that you'll see, is probably a bit of a challenge. But I guess the first thing I wanted to say is that your context is critical, and Christian and I have spent a little bit of time and written some work comparing the value of deep roots in, say, an environment like Denmark, where you can see here, you've got, this is rainfall and evaporation. It's wet a lot of the year, the crops are growing for a lot of the year, winter wheat can yield 10 tonnes per hectare. This is the context that Christian works in, mostly trying to capture nitrate before it leaches into the groundwater in a system like that. If you compare that to where I come from, now you see the deficit between how much rain you get and how much evaporation. We can only grow a crop in this small period essentially in the middle of the year. We struggle to get 3 tonnes per hectare of wheat, and so my context is really capturing deep water to help these crops fill their grain at the end of the season. So again, whatever your context is, it's important to be thinking about the systems issues around capturing value from the deep roots. So a little bit of background to this Australian case study. I guess I was inspired to start working on this by the observation that even though I'm in a very dry environment and crops are dying at the end of the season from water stress, they're often leaving available water behind in the subsoil. And this was sort of written about by John Cassiora and others. In the 1990s, and Peter Gregory would remember this, he was working in Australia at the time, we were worried about salinity. We were worried about water going through the profile in our wet winters, bringing salt up with it when it hit the water table. And we were busily planting lucerne all over the country to try and de-water profiles. And so, we had a period of really looking into how we could manage this deep water and use it and get it out to stop water tables rising. Then we hit the 2000s and what we now call the millennium drought, and since then we've had climate change biting, and we've really sort of had to change our focus into how to make value of this water, and what do we do once we've used the water? How do we get the soil to wet back up again? And so the case study I'm going to talk about, I sort of summarise as trying to use more of the soil and more of the season in the context of this quite dry environment. So we started many years ago, as I said, inspired by John Cassiora, to say, well, is this deep water really useful? Or is it really, can the crops not really get it? Are they shutting down? Are they stressed too much to sort of make use of this deep water? And so we did a lot of experiments with rainout shelters where we could specifically wet the soil to different depths, isolate the deep water and put a value on it. And that told us that this deep water was extremely valuable. Every millimetre that we could get from the deep soil in some experiments was worth 60 kilograms of grain per hectare. Julianne Lilly then did some simulation studies, and we imagined if we could breed wheat with deeper roots or more effective roots, would that convert into more yield? And the simulation studies suggested that it could, but it was extremely variable depending on how the rain fell. But on average, a millimetre of water from down here, around 2 metres, could convert to 35 kilograms of grain per hectare. So an extra 12 mils of water from down there could give you half a tonne of wheat, and that's very significant in our context. So this was worth chasing. How do we get there? Well, there's all sorts of management strategies you can think of to get more roots at depth. Sowing earlier, sowing more crop, more plants per square metre, doing deep tillage. And Anton Wasson yesterday already talked about a lot of the genetic approaches that we were looking at. Now, I think we should stop thinking about either or, and we should be thinking about the interaction between the genetics and the management that we need to get deep roots. And as I'll show you, we have been using genetics. It's not the genetics of the root system, it's the genetics of flowering time and phenology. But it's been interacting with management very effectively to utilise deep water. So in Australia, what we know, here's our year. It's too dry to do anything in the summer. The farmers wait for rain to sow crops in May sometime, and what we know is that wheat roots will grow down at about 1 to 1.2 centimetres a day till anthesis, which sets the sort of depth potential, and then we go into the dry summer and the grain fills. We need to keep the flowering time pretty constant up because we get frost here and heat stress here. So this is sort of the system. Now, pretty simply, we could try and breed wheat that can grow roots down more quickly, or we can simply sow the wheat earlier and get the roots deeper by having a longer vegetative phase. And this is the sort of idea that we've been following. But of course, that sounds very simple. Let's just sow the wheat earlier. But of course, as I said, we have traditionally had to wait for rain to sow this crop, and that rain under climate change is disappearing. We need to make sure flowering still occurs at the right time to avoid frost and heat. So we have to sort of think about the system that goes around this opportunity. But we certainly could show that sowing wheat, and these are now winter wheats or semi-winter wheats, sowing them earlier did in fact get deeper roots. You can see here's a winter wheat sown in March compared to a spring wheat, typical spring wheat sown in May. This is the root length density on an exponential graph, and indeed, we only ever used to measure roots to 1.8, but you can see this crop had significant roots down at this depth and utilised an extra 20 millimetres of water from that depth. So this earlier sowing of wheat could get more roots there, was using more water, and this was converting into higher yields. So I want to summarise now a sort of a 5-year project, which we call the Water Use Efficiency Project, and I want to summarise it in the context of this early sowing opportunity. So the wheat system in Australia, very briefly and pictorially, a lot of people are growing continuous wheat. They'll graze the sheep on the stubble in summer, and then they'll burn and cultivate the soil, plant the crop in May, with usually a spring variety of wheat. So that's the sort of typical system that occurred across a lot of Australia, and the mean wheat yield across the country, 1.6 tonnes per hectare at that time. Now, we did a lot of modelling and a lot of experiments to demonstrate that you can change different things about this system, and if you change things one by one, you can get some improvements in yield, but as I'll show you, if you change the whole system, that's when you get the best benefit. So, for example, if we shift from continuous wheat to having a better rotation, we could take mean wheat yield from 1.6 to 1.8. So it's a significant increase in yield, but it's not exciting. If we, instead of letting sheep graze on weeds in the summer, that are obviously using water, if we keep summer weeds controlled with herbicides, and that's all we do, so these are just single changes to this whole system. So we're still growing continuous wheat, but now we control the summer weeds. That's giving us a somewhat bigger yield impact from 1.6 to 2.4. So storing that summer moisture is becoming more and more important. If we shift to no-till, but we don't do anything else, so we still grow continuous wheat, we let the sheep graze, but all we do is change from burning and cultivating to no-till, once again, a significant yield increase, but not exciting. What about if we just sow wheat earlier? Okay, we do everything the same, but we sow wheat earlier. Well, it does seem to give us a bit of a yield improvement. But if we continue to use a spring variety, we don't really get the benefit from this earlier sowing. But some new genetics we have, including longer phenology and varieties with a long coleoptile that allows us to sow into moisture much earlier than we normally can because we can put it into stored water. If we do that, but we don't do the rest of this stuff, okay, so we just make that single genetic change, we actually go backwards in yield. But if we put this whole system together, the yield benefit, the predicted yield benefit and what we went on to demonstrate takes us from 1.6 to 4.5 tonnes. Because we now have a healthy root system, we're storing moisture in the summer with no-till and controlling weeds, we're sowing earlier into that moisture with a longer season variety, and that whole system takes us to 4.5 tonnes, and we've now got farmers achieving 4 tonnes in some of these environments. And even if we just look at the years of the millennium drought, so if we assume climate change is coming, even in those years, it was doubling our predicted yield benefit. So this is an example of if you just have a long season winter wheat that can get deeper roots, and you put that into the system without changing all this other stuff, you really don't see much benefit. In fact, it went backwards. But with the system around it, huge yield benefit. Now, Australian farms are 2,000 hectares. It takes 20 days to sow the farm. And if you can start sowing earlier in one paddock, it means all the paddocks or fields on the farm get sown earlier. So there's a knock-on effect across a whole farm of a benefit. Even if you only start sowing some of these fields earlier, all the fields get a benefit from being earlier. And this is an incredible scaling up benefit. And we've published a paper recently on this, and these are a whole lot of different areas around Australia, but the only thing that you need to take home is in the subtropical north, it really isn't a system that works very well because of the particular physiology there. But in southern Australia, in temperate areas, and particularly in the higher rainfall areas, above 270 millimetres of growing season rain, the average farm yield, this is the average yield benefit for a 2,000 hectare farm, is huge. And there's almost no downside to this technology. And overall, if you add it up, if you do some heroic scaling up across the country, it's quite an enormous increase in potential productivity. And much of this benefit is coming from deeper roots accessing that soil moisture. We've just finished another project showing all of the same opportunity occurs for canola. In much of this sort of southeastern area where we grow canola, if we can get canola sown earlier, which is even more sensitive to stress than wheat, and it can access this deep water, there's also benefits. So what I'm talking about is simply moving the sowing from May back into March or April. Keep the flowering date, this is the optimal start of flowering. Keep the flowering time the same and the harvest time the same. We're just changing the phenology of the plant so that we can sow it earlier. This again has enormous benefits. And here's an experiment that we've been running in the last 2 years just to show this. So here's two varieties of canola, one sown on the 4th of April, one sown on the 7th of May last year, which was a decile 1 year. It was a complete drought post-July. And at harvest, when I measured the soil moisture left in the profile, down to 3.5 metres, you can basically see the early sown variety in blue here has dried the soil below 2 metres much more effectively than the later sown variety. We measured the rooting depth, and indeed the later sown variety only got to 2 metres. This one was deeping much more deeply, and there was an extra 32 millimetres of water taken out down here, which gave us over a tonne benefit in yield. And based on the sort of root observations, the roots were growing down at about 2 centimetres a day in this experiment. So this year, we've just harvested this year, and I repeated this experiment. And this year we got ourselves organised with a soil corer that could go to 4 metres, a bit more reliably. During the season, we found canola roots were growing down old lucerne channels. So this is an old lucerne root in a biopore. This is canola at 1 metre. Canola occupying and utilising the same biopore. But at the end of this year, we had canola roots at 3.6 metres and even down to 4.6 metres. I don't know if you can see those canola roots, but we take these and wash them out, look at them under the microscope, and we can identify them as definitely being canola roots. So again, the canola was growing down at somewhere between 2 to 2.5 centimetres a day before flowering, and then 1.2 centimetres post-flowering. So both wheat and canola, sown early, can get their roots deeper, utilise soil moisture and convert that into yield. Another benefit from these crops in Australia is that most of our farmers have sheep on the farm, and they can be grazed in the winter. And if you do this well, you have no impact on grain yield. So instead of sowing in May and harvesting grain, you're sowing in March and April, you're grazing through June, July and August. If you take the animals off before the crop is reproductive, all of this is just extra profit, and they yield the same as an ungrazed crop. So this is an an added benefit to growing these things early. And the grazing has no impact on the rooting depth. We've checked that. So it doesn't stop the rate of root growth, even though you're grazing them off in the winter. So the question is, this is all great, but so having dried the subsoil out with my wonderfully high yielding canola and wheat crops, and leaving this really dry subsoil in Australia, what's the chances I'm going to fill it up again? So, you know, in Australia, the farmers call this the bucket, the soil water holding capacity is the bucket, and what's the size of my bucket, and am I going to be able to refill it? So to answer this question, obviously the chance of refilling it is much higher in a higher rainfall environment and on a soil that perhaps doesn't hold so much water. You're more likely to fill it to depth. I had a 28-year tillage trial with all of the data I needed to validate a crop simulation model, which we've done here. So this is a crop simulation model started in 1990 and validated against 28 years of data. So the line is the model, the points are the measured values, and you can see both mineral N, soil water, biomass and yield. We got the model to a point where it was doing a pretty good job of simulating what we saw, which then allowed us to ask, well, what would have happened at this site where I was mostly sowing in mid-May? What would have happened if I had been adopting this strategy of early wheat and early canola? So, in other words, what's the predicted effects of this new agronomy, summer weed control, sowing wheat early and canola early, and then I threw in some nitrogen fertiliser just because of these high-yielding crops probably need more nitrogen. And just to show you a summary of that work, this was the measured yields over 28 years. Average wheat yield was 4.5 tonnes, canola 2.9. My weed control was already pretty good, so, you know, assuming perfect weed control, I didn't get much of an increase in either wheat yield or canola yield, a little bit. If I sowed wheat early, you can see I took the average wheat yield from 4.7 to 5.6, but I stole a bit of yield from the canola, not a lot, but growing those longer season wheats and using more water was actually taking a little bit of water and or nitrogen from the canola, and so its yield went down a little bit compared to the early canola. If I grew early wheat and early canola, the early canola yielded a bit more. I only took a little bit of yield from the early wheat. So basically, you know, this system is still more productive than what I was doing. But clearly, nitrogen had become a huge limitation in this system, because if I added an extra 50 kilograms of nitrogen every year, I took the yield to 6 tonnes for wheat and 5 tonnes for canola. So clearly in this system, the canola was getting sort of highly nitrogen deficient. And so this sort of shows with a validated model that in this environment, which is relatively wet, adopting this system doesn't create legacies that are not worth, you know, it's still worth adopting this system. But of course, if you move further west into drier areas, that's possibly not likely to be the case. So that work was all done around here. And we've now got a new experiment with 4 sites further west in drier environments on different soils to test this idea of how to manage these legacies and of deeper rooted crops utilising more water in the farming system. And one of the things we're doing is we're putting them in rotation with shallower rooted crops that use less water, like chickpeas and lentils, because by sequencing the crops in that way, you know, in drier environments, you can probably still have these deeper rooted crops in the system, and they can still be profitable. And that's the sort of idea behind this new project. So that's the story. That's the story from Australia, I guess, about how yes, we had deeper roots. Yes, we can get more water out, but we really had to change the farming system in order to make that. To get the most out of that. So I guess then the question is, and Peter Gregory asked this question, well, how many deep soils do we have in Australia? And if you go to our sort of current soil and landscape grid, it'll convince you that the soil's only 1.2 metres deep everywhere, and that's basically because the soil survey guys only had 1.2 metre cores. So I mean, I know I've actually worked on sites where I know I've got roots to 3 metres, you know, at a few sites in Australia. So I said, well, what's going on? And they said, well, we only had the soil survey to 1.2. So, however, they're getting better at this, and now they've been working on developing a continental soil thickness map, which, you know, they talk about a pedalith, which I think Peter called it something else, but it's the stuff above the bedrock basically that might be rootable. And they've been using, so this is Geoscience Australia, so that's a sort of federal government organisation that deals with geology. They've got outcrop observations, 14,000 from around the country where, you know, they can see how deep the soil is. And all of the guys that dig bores for water often take observations of, you know, when they're hitting soil or rock or whatever, and there's 355,000 of those. So these guys have collected all this information and then done some fancy geostats and modelling, and now, you know, these blue areas are areas of Australia where the soil is likely to be deeper than 3 metres. So, so I guess, you know, there are places in Australia where this opportunity to go deeper than 2 metres definitely exists, even in a dry place like Australia. But the farming system that you need to, you know, overlay onto this opportunity, you know, is you have to really think it through. And obviously, if you're in a wet environment like Denmark or in the higher rainfall areas of southern Australia, then you know, there's a much bigger likely benefit. So I guess that left me wondering, and I've come full circle back to Peter's question on day one, which is, you know, where in the world are the deep frontiers? And my question then is, do we have the production systems to take advantage of them? That's the end.